Let's talk about the foundation, the fundamentals that form the science behind modern temperature control. It's all about viscosity. All liquids change viscosity as a function of temperature. As we can see from this old graph, water changes viscosity by a factor of 2 to 1 from 10 to 40 degrees C. Now, we don't think about a cup of coffee as being thinner than a glass of ice water, but it is. All coating materials follow this same pattern. This is why we often see viscosities specified on a data sheet is usually given at a specific temperature, 25 degrees C or 77 F. So here's a typical paint curve. And it's the curve that we're used to seeing. It's nonlinear. The viscosity falls as the temperature increases, and vice versa. Valspar specifies that this should be run at 26 seconds. And if we take 26 seconds and extend it over to the curve and down, we can see that that corresponds to a temperature of 28 degrees C. Here we see the viscosity versus temperature curves for 7 paints. They're all the same. The only difference is the color. But with color comes different pigments, different binders, different additives to make the formulation work. And we can see that that results in a very different temperature versus viscosity performance. If we want these to all run at the same 26 seconds that we were talking about, we have to change the temperature of each paint. The black, for instance, will have to be run at about 21 degrees C. The muslin and warm beige will have to be run around 24. The charcoal is going to have to be run at about 26 and a half, and the putty is going to have to be run north of 29 degrees C. How do we handle that in our manufacturing process? Now, let's talk about spray for a minute. All spray processes are different, and yet they all boil down to this basic configuration. Here we can see we come from a supply, we run through pumps and regulators and whatever devices are necessary to maintain flow and pressure at the nozzle. But there's only one temperature that really matters to the finished quality of the part that we're painting, and it's the temperature of the paint leaving the nozzle. So what factors actually affect the temperature of the paint as we're applying it? Obviously, the area ambient is one thing. The storage temperature, what temperature do we bring it to our process at, is another. Then there's the volume of the paint in the source container. Obviously, a 200-liter drum is a much smaller thermal mass than a 1,000-liter tote. And then there's the flow rate at which we're circulating it. And that rate determines also from the path. Where is it routed? Is it up over the ovens? Is it in the truss level? Is it down in a trench where it's cooler? All of those factors contribute to paint temperature when we apply. And then there's the pressure setting. If we're circulating at pressure, we have to use a pump, and that pump and the size determines how much energy is added to the paint. And energy added equals heat. And then there's other things in the system. There's back pressure regulators, there's nozzles, there's just simple pipe curves, all of which add shear. Shear adds friction, and friction, again, generates heat. So our goal has to be to control the viscosity of the paint at the point of application, which in spray systems is a nozzle orifice, as we've already seen. We need to control at the point of application, and to us, point of application is both a philosophy and a process. The process starts by thinking backwards from everyone else. Then, acknowledge that the only paint that you have to be concerned about is that which is actually being applied to your part. Next, start at the point of application and work backwards, adding temperature control until all conditions can be satisfied, and then stop. That's going to give you the optimum temperature control and assure that you're always dispensing at the proper temperature, which is to say, the proper viscosity. Next, we'll talk about some of the devices that are necessary to actually maintain temperature all the way to the point of application.